Good morning, everybody. How we doing today? We'll start the day with a little Led Zeppelin for you. Hope you guys are doing well. This posting is going to come out for Friday morning, March 27th. It really is just a short go over of the answers for the Mighty Mouse Hardy Weinberg assignment. Without further ado, let's get after it, everybody. So when we look at this assignment, this is really what as I was talking with Amanda and I spoke yesterday, she had a couple of questions. And as we spoke, what we really want to make the transition to you guys is not just the using of the formulas, the P plus Q and the P squared plus 2PQ plus Q squared, those two equations. That's kind of the first step, is to understand the math behind the work. But now we take it to a step where we're really looking at a population. And when we look at a population, we look at any changes it may have gone through over time, and we compare those changes to that hypothetical Hardy-Weinberg population. And if we see significant differences from what we would expect for that Hardy-Weinberg population, remember that Hardy-Weinberg population is one that does not change. There's no evolutionary forces acting on that population. So when we compare a potential changing population to a hypothetical one that doesn't change, if we see a significant enough difference, that means that evolution is occurring. And then we pinpoint what is the cause of that change. And so that's what this is walking us through, is kind of a semi-simplistic look at a population, but a very realistic one just the same, in that we're looking at this hypothetical species of the mighty mouse that lives in the American Northwest. And it's really coming down to the coat color of these mice. They are dark for dominant. And a question or two came up in one of the classes, I think sixth period, where it was, we weren't certain of which was dominant. And it's telling us here that dominant D is dominant. I'm saying dominant a lot, but dominant D for the dark phenotype is there, and the light recessive is right here. So all an individual needs is one dominant D allele, and it will be a dark colored mouse. If it's recessive homozygous Ds, then it will be the lighter colored mouse. So that's all the information that we're given. And as we walk through the Hardy-Weinberg principle, what I have stated in here, the answers, and let me zoom this a little for you guys. What I have stated in the answers are those two formulas that we've been working with. And a reminder that the Hardy-Weinberg principle serves as our null hypothesis. If observed genotype frequencies don't match the expected genotype frequencies, then that population is evolving, it's changing. Okay, remember, we're not heading towards some perfection of species. It's just change in a population that very often is occurring due to environmental pressures. So as we look down, we remind ourselves of the 5 assumptions of the Hardy-Weinberg principle. And we say, okay, those things that keep a population steady without changing means that there's no natural selection. There is no random allele frequency changes due to genetic drift. There is no gene flow, which we remind ourselves just to separate genetic drift and gene flow. Gene flow is migration. Any type of something moving into the population or anything moving out of the population that can essentially change allele frequencies in the gene pool of that population. Another assumption is that there's no mutation. There's nothing at the genetic level, the DNA level, that's changing the genetics of that population. And finally, the 5th assumption is that there is completely random mating, that there isn't any sexual selection going on, that there isn't females choosing specific male mates based on the amazing colors that they put out or the big chest that they puff out because they're big and strong gorillas, or whatever the case may be. The Hardy-Weinberg principle tests that if the observed genotype frequencies match the expected genotype frequencies. If they do, then the population is not evolving. If there is change, then that population is evolving. And I can change my typos luckily as I go. So as we look down, we're sampling this mighty mouse population in Oregon, and it gives us specific numbers: 53 homozygous dark, 49 heterozygous dark, and 76 light mice. So we can throw these numbers right into our table. 53 big D big Ds, 49 big D little Ds, Ooh, there's another typo. Go me. Sorry, guys. And 76 little d's. And all we need to do with that is total up our total population. So if we punch into our calculator real quick, we say 53 plus 49 plus 76. We have 178 total mice. And a few of you may have been confused later on, maybe even in number 3, where I threw out the number 356. If we have 178 individuals in this population, and every one of those individuals has 2 alleles for this coat color that they carry, all we have to do is take that 178 and multiply it by 2. That 356 is the exact number of alleles in the gene pool for the coat color trait. So that's where that 356 comes from. So all I did here was take my 53, and we just figured out what's our frequency of 53 out of 178, our number of individuals. So 53 divided by 178 gave us our 20, I can't really move that, but our 0.298. Okay. I did the same for the other two to figure out the breakdown of the population based on genotypes. If we really think about it, then we're saying, okay, that means that big D, that was, that's not going to work. Let's go here. That's our P squared frequency. Big D, little d, that's our 2PQ. And little d, that's our Q, I can do this, squared. Okay. So now that we know those are specific counts. We have exact counts of every single allele in this population. So what might have tripped some of you guys up as I look at the work later on today, since I'm filming here on Thursday, as I look at your work, some of you may have tripped up on this and gone straight to taking your Q squared and square rooting 0.427. When we have the exact number of individuals for every genotype, we can basically count the alleles. So follow with me as I go down to number 3. It says, what are the allele frequencies? So we're solving for P and Q, but it's actual observed numbers. So for the big D allele, I can go right up to my individuals that are big D or homozygous. I have 53 of them. So every one of these 53 mice has 2 big D alleles. So if you look down here, I take my 53 individuals times 2. So that's 106 big D alleles right here in this population right here. My heterozygotes, they have 2 alleles, but only one of those alleles is a big D. So of those 49, I just add 49 more big D alleles. So I took my 53 times 2 for those individuals up here that are carrying 2 big Ds, and then I just took one of each of these 49 individuals, and I added that all together. So 53 times 2 is 106. I added another 49 to give 155. Divide that by that 356, which is the total number of alleles in the population. And that gives me a p-value of 0.44, or 44% of the alleles in this population are the big D. I did the exact same process down here for the little d's. I looked at the homozygous recessive. There were 76 of them. That means those 76 individuals all have 2 little d alleles. So I took 76 times 2. And I added to that just one each of those 49 individuals that are heterozygous, since each one of them is only carrying 1 little d allele. That gives us 56% of the alleles in this population. Once I divide by 356, that gives me 56% of the alleles will be the little d, or that's my Q value. And I can even add that on here. We want to remind ourselves that P is 0.44, and 0.56 is Q. Okay? All right. So what we want to do with this information at this point is we want to make sure that we figure out our expectations. And so as we do our work right here, we want to take our P and Q values. that were taken directly from the allele frequencies, the genotype frequencies up above, we want to take those and just plug them in now into our p squared and 2pq and q squared. This is telling us that based on these allele frequencies, these down here should be the expected genotype frequencies. So we punched in 0.44 and squared it to get p squared, meaning that if this is a Hardy-Weinberg population that's at equilibrium, 19.4% of the population should be homozygous dominant. If I plug in 0.56 for Q squared, that gives me 0.313. And what that tells me is 31.3% of the population should be homozygous recessive. I do the same to figure out what should the expected population be for the heterozygotes. 2 times P 0.44 times Q 0.56 gives us 49.3% of the population should be heterozygous. So these are expected values, and I want to even just kind of bold that to remind us. What we did up here in 2 and 3, these are actual observed, this is what's going on in this population. And that's what I think, as we're learning this material, this is what we struggle to understand. And it's not going to necessarily be crystal clear by the end of this lecture, but hopefully this gives you some thoughts. 2 and 3, this is the actual observed what happened in that, or what's going on in that population right there. By taking the P and Q from that observed and just plugging into our P squared, 2PQ and Q squareds, we're getting our expected genotype frequencies. So as we go down here, we can then compare. My expected frequencies, this is what I just did in number 4. My observed, this is what we did when we filled in the table up above in number 2. Now all we do is just compare. Are those numbers the same? Are they close? Or are they way freaking different? So in this case, big D, 0.194 is the expected, or 19.4% of the population should be homozygous dominant according to the P and Q values that we have up here. What we observed is 29.8%. That's a pretty big difference. There's a 10% difference in the numbers of homozygous dominant dark mighty mice. As we look on down, our heterozygote, what did I get wrong here? This is not right. This is flipped, guys. I hope you guys figured it out and I just screwed up in my filling out of my answer key. My numbers that I have here, this is my homozygous recessives. And this is my heterozygotes. Yeah, that seems more right on. But let's see. Actually, yeah, I screwed up my answer key. I'm kind of fixing on the fly here. My heterozygotes were 0.275. So what we're going to do is we're going to flip this. My heterozygotes were observed to be 0.275, but when we did our calculation, we expected 0.493. My homozygous recessives, we got 42.7% of the population was homozygous recessive. So I can put that right here. Let me see that again, make sure I get it right, 0.427. But we expected from our calculation up here for Q squared, we expected 31%. So apologies for the mix-up of my lines here, guys. But we should see, what we see is very different numbers from what we expected and what we observed. So the observed and expected frequencies are very different. This means that the Hardy-Weinberg equilibrium is not upheld, implying the population is evolving and that one of those assumptions, one of those 5 conditions is being broken. And so as we look on down, we can see just big differences amongst all of them. A difference of about 10% from the homozygous dominants, a difference of about 11% for the homozygous recessives, and a difference of about 22% for the heterozygotes. Down below, number 6 says, in Oregon, where this population occurs, there are areas that contain light rocks and those that contain dark rocks. Explain how this information and figure 2, which is just a picture right here, relate to your answer in question 5. And it's basically saying what assumption of Hardy-Weinberg is potentially being violated to cause these difference in numbers of what we're observing versus what we would expect if a population is just staying the same and not changing. So it says figure 2 shows that light mice and dark mice are not well camouflaged on their opposite colored rocks. So it all comes down to camouflage for these mice. Natural selection, therefore, could be acting on those alleles by just predation. If there's snakes in the area that prey on these mice and this light colored mouse jumps out to them, they're going to bring that population down, and that will give us very different numbers than what we see up above. So that's where we see here, as we looked at our expected heterozygotes, we expected almost 50% of the population to be heterozygotes, but it was way less. We expected a lower number of the light mice, but we actually had a lot more. So that leads to this heterozygotes could be much less abundant because emigration is selected against, because they're not moving out of the population so much. And so we just want to keep in mind this understanding that what I really want us to pull from this, what I really want us to see from this, is the comparison of these numbers and how we got to this point. So I would really review the steps that we took here as you look at these answers. And I may clean this up and flip these two and just go from homozygous dominants to heterozygotes and then to homozygous recessives so that we can really see that progression from one to the next. But that's everything here. Feel free, guys, as this will be posted Friday morning, feel free to message me and we can Google Meet if you need any further clarification on this material. As we'll see this on next Wednesday's quiz. Thanks, you guys, and let's finish off with just a little more Led Zeppelin as I find the stop button. Happy Friday, everybody. Miss y'all lots.